Hello. Now we have just a few notes to take on dilations. Since we've already done work in transformations, this is actually going to go very quickly. We're going to take some information from our transformations, some information from our similar polygons, and put them together, and we have dilations. A dilation is a transformation that enlarges or reduces the size of a figure. This is not new. We've already used these words. And in fact, we've already used the words for the original figure. Remember, that is called the pre-image. And the transform figure is also called the image. When we're working with dilations, we're always using the scale factor, not the similarity ratio. And just as before with similar polygons, that describes a change from the pre-image to the image, from the original to the transformed. If the scale factor is greater than 1, you should remember that we actually end up with a larger image from your notes we just did, and that is called an enlargement. If the scale factor is between 0 and 1, then the figure is going to decrease in size, and that is called a reduction. I haven't really talked about negative scale factors. You don't see them so much with similar polygons, but when you do coordinates, you could have negative scale factors. As before, for similar figures, you will always have angles that will not change. The angles will stay the same under dilation. So the rule for dilations is really simple. If you look at this, this looks a little bit like our rules that we were doing for translations and reflections. You just take the scale factor and you multiply the x-coordinate of the pre-image by that to get the x-coordinate for the image, and you multiply the y-coordinate of the pre-image by the scale factor to get the y-coordinate for the image. So in example 1, I went ahead and looked up the coordinates for A, B, C. A is 3, 5, B is 1, 2, C is 4, 2. To get the coordinates for the dilated image, I need to know the scale factor, and it is 2. So I'm going to multiply each coordinate by 2, and you can see my work here on the side. 2 times 3 is 6, 2 times 5 is 10, 2 times 1 is 2, and 2 times 2 is 4. So all of these coordinates come from these coordinates up here. The rule is you take your original x and your original y and you multiply each coordinate by 2, so that it's 2x, 2y. In example 2, it's another triangle, and I wrote down the coordinates. D is -4, -2, F is 6, -4, and E is -2, positive 8. So writing these down here, and now my scale factor is a half, and you can multiply by a half. -4 times a half is -2. It's actually a little easier to just divide by 2. And so I took all of these blue coordinates here and divided them by 2 to get these coordinates for my image. So the rule is still 1/2 times x and 1/2 times y. I could have also said x divided by 2 and y divided by 2, and that would have given me the same answer. Example 3, coordinates for A are 4, 6, and coordinates for A prime are 12, 18. So I can do this, find the scale factor just like I did with similar polygons using a point instead of sides. So I'm going to take this number that I know for A prime, the 12, and the 4, and make a ratio from it. 12 over 4 is the same as 3 over 1, which is 3. I could have done it with the y coordinates. 18 over 6 is also 3, so it wouldn't matter which set you worked with. Now, I can also apply the scale factor to lengths. So if BC is 3, then B prime C prime would be the scale factor, which is also 3 times a 3, which gives you 9. Here they tell me A prime C prime, this large side here, is 10.8, and they want to know what is the original size of the pre-image. So I can go backwards. Going backwards, I would divide. So 10.8 divided by 3 is 3.6. Now, angles in similar figures are always congruent, so there's no need to use the scale factor. If angle BAC is 50 degrees on this apex angle here, then the angle in the image will also be 50 degrees. Now here they're asking if the two triangles are congruent or similar, and they are not the same size, so they can't be congruent, but they are the same shape, and they are similar. For examples 4 and 5, the image of the point -2, 1 under the dilation with center 0, 0 and scale factor of 4 is what? By the way, I may not have mentioned it before, but all of the dilations we're doing are about the origin, and that's why it's so simple where you just multiply the scale factor. So when you see with center 0, 0, don't let that throw you off. That's just a normal dilation about the origin. So all I have to do is take both of these points and multiply them by the scale factor of 4. -2 times 4 is -8. 1 times 4 is 4. And so there's -8 and 4. Example 5, now they give me the point of the image, and they give me the point the pre-image and the point of the image, and they want to know the scale factor. So I have to do the image on top of the pre-image. So 2 over 6 is 1/3. And I can also check it with the y-coordinates. -5 over -15 is also 1/3. And our last example, now they are giving us the image coordinates. They're telling us the scale factor, and they say, okay, what's the original pre-image? So we're going to go backwards. Although I actually set up an equation on here, the other way you could do this is just divided by 1/4. But let me show the equations because it's a little more rigorous and you need to practice your algebra anyways. Well, if my original points are x, y, then x times the 1/4, the scale factor, has to give me 3. Well, then I can divide both sides by 1/4, and 3 times 1/4 divided by 1/4 is the same as 3 times 4, or 12. Doing the same thing for the y-coordinates, I end up dividing 2 by 1/4, which is the same thing as 2 times 4, and I get 8. So my original coordinates are 12, 8.